few things. In this one, we'll be focusing on doing this sort of limit like we see here. And it looks quite complicated. The third root of n plus 1 minus the third root of n minus 1 over the third root of n plus 3 minus the third root of n minus 3. And there's many comparable cases that look similar like this, whatever that is, whether if we see it as a function or a sequence. In either case, we'll use some algebraic manipulations to get the limit of this. And there will be a trick used, so that's the main point here. So all the details aside, let's get into it. So we have a third root of something of a first degree polynomial, and from that subtracted a third root, and the same in the denominator. And now this is at this point quite inconclusive, so we'll make many steps to get somewhere. And the main sort of trick here will be we will use sort of this identity that think to the third minus a to the third minus b to the third equals a minus b in the first degree times a squared plus ab plus b squared. And the thing is, there's not 2ab, but it's just ab. So the identity goes as follows. And I mean, this works also on higher orders, but there we sort of use the binomial theorem, but we remove the middle coefficients. So for a4 minus b to the 4, we would have, again, a minus b, that would be same. But as for this one, we would have this. Alright, so we would take sort of the a minus b to the third, but here usually would be 3 and here also 3. But in this case, in this identity, the middle coefficients are not there. So that's a catch. One can check it by multiplying it back and seeing that it gives this. So it's sort of like binomial coefficient with the middle coefficients removed. And so, the coefficients removed. Alright? I mean, with the a third minus b third, it's easier to remember. Here's already a little bit more complicated. Fortunately, we're dealing with the first one in this case. So that's the main trick that will be used, the main trick here. And how is it going to be used? Well, we imagine the n plus 1, and in the third root, that's the a, and the b is the other one. So if we say that, well, sort of we do n plus 1 is a, and the same thing we'll do for the denominator later in a second also, but let's now take care of that. Well, then we can say this. Alright, but we want to express it for a minus b, because a minus b is kind of the original according to this substitution. So we will get a minus b equals, divide on both sides by the parentheses. And that gives that this subtraction will turn into, and now we'll ignore this because that was a middle reminder of the, or a mention of the trick or the identity. So if we want to rewrite it, we will actually get n plus 1 minus n minus 1, only the insides of the roots. That's it. Now we're still doing the limit. We're just rewriting the algebraic expression inside the limit. Divided by, and there's actually going to be an even bigger division, but it depends how we want to write it. Divided by, and we're still dealing just with the numerator. A squared, well, that will be the third root, but the argument is squared. So the algebra does that, plus add ab, which will be multiply the two arguments of the third roots on the numerator. And plus third root of n minus 1 by itself squared. So we get that. But now we also have to divide all of it and do it with the denominator. And the denominator will be the same story. So we'll manipulate it the same way. Alright, so what I can do is I can multiply by the reverse. So just follow the same pattern, but fill in n plus 3 and n minus 3 for the same stuff. And I will invert it because multiplication by inverse of the fraction is like division by it. There's not that much space vertically on the board, so therefore we'll do it that way. So I would have n plus 3 minus n minus 3. And so now I'm dealing with the denominator. So then the same thing, because we have a very symmetrical sort of fraction, so we can really rely without much focus on just doing the thing twice with slightly different numbers. That's kind of an advantage here. That's also how the example was created, sort of in this manner. We train the identity without getting into unnecessary troubles with some small mistakes. So this whole thing is the argument of the limit now. We rewrote it. And now we can change this very much. So n and n, this is minus. N cancel, but we have 2 left. And I will replace the numerators, denominators here in a bit. This cancels and adds. So we have 2 over 6 times the remainder of the fractions here. We have this, which we can rewrite as, I'll go a little bit slow still. Alright. And then we have third root of, this gives n squared minus 9. And third root of, this is another line, it intersects a bit, but we have to be careful. It goes a little bit into the denominator of the previous line, but we're already rewriting it once again, and this is all the limit of. I could actually already take this constant term outside of the limit. But anyway, now we want to actually prove these two things will turn out as 1 over 1, but we'll see in a second. We have to continue with this to properly kind of prove that. So n squared minus 6n plus 9. Alright, so we have that. And then the denominator will be this thing. Well, we'll do the same thing. Third root of n squared plus 2n plus 1 plus third root of n squared minus 1 plus third root of n squared minus 2n plus 1. Alright, this one. Well, let's try to separate it out a bit. It's above the 3 actually. So this is complicated, but let's not lose focus too much. So this 1/3 can go outside of the limit. And the remainder here is this. And what I'll just try to separate the rewritten expressions by a line so it's not intersecting. Alright. Now, to prove that the stuff that's left is also kind of a constant result, we can take out this n squared outside of the root, and that's done this following way. If you take the same degree root and take the highest term, the n squared, I can rewrite this third root as third root of n squared times third root of the original root, but divide each term by that thing that was taken out, n squared. So 1 plus 6 over n plus 9 over n squared. These two terms will actually eventually go to 0 thanks to, you see, this will be a dominant term and this will be a constant term, but 6 over n will go to 0 and 9 over n squared will go to 0. Then we do the same for the remaining ones. So again, take out the highest term, which is always n squared. That's what's easy in this one, sort of. Alright, so for this one, it's 1 minus 9 over n. This one is simpler. And third root n squared again, like this. 1 minus 6 over n plus 9 over n squared. These are sort of redundant. We see their lower degree and they will go to 0. The same thing will be done for the numerator, sort of. So we get 1 plus 2 over n plus 1 over n squared. If there's a mistake, it doesn't really matter that much. We have to, of course, always pay attention to not get into wrong results. But still, I kind of said how it's going to end up anyway. So, I mean, of course, in explicit solutions, again, with another example, definitely be careful. But yeah. So we have this. Here it's really much about the idea, but still we can try to have it correct. So third root and take out this, minus 2 over n plus 1 over n squared. Now everything that has a n to the minus 1 or lower degree, we can cross out as limit going to 0 for that concrete term. So what we get is, okay, 6 over n goes to 0, constant over n as n goes to infinity, alright? The limit, all along here is of course meant to infinity. I mean, if you just use limit, usually it's meant s goes to infinity. It's the kind of default setting, if you don't mention explicit, alright. If 6 over n goes to 0, 9 over n squared definitely goes. The same applies to everything n minus 1 times constant and lower. So this, and all these, they will just stay the constants in the roots. So we have 1 times limit, but now we see it's the same stuff here and here. So that will actually eventually cross out very easily. And we have third root of 1, third root of 1, third root of 1. So in total it's 3. This is third root of 1, third root of 1, third root of 1, 3. Because the rest cancels out, so there's this one left, this one left, this one left. Any root of 1 is 1, and we add them. I just isolated out the third root of n squared here, outside of it. So that's what we have left. This is 1, and so the constant multiple before the limit is left. So here's the result. I mean, of course, with some more repetition of similar examples, one can make bigger, faster steps because one kind of found out the pattern, alright? Or one can choose not to write out the lower terms when we're multiplying here, because if we take out the n squared, we see the highest degree term there, and that can be focused on, and it could be kind of taken as for granted that the other ones are lower, so we don't have to explicitly write it out. But still, it's perhaps good practice like that.